Hi guys, welcome back. Time now is 12 o'clock 32. It's 10 o'clock 32. And we begin now today's morning session for my study live stream. And welcome back, you guys. And this live stream, we're gonna try to not leave Tish and try to speak clearly as we could, and to in order to soon satisfy the earning requirement and to make this platform confirmed and make my YouTube channel rentable. And so that's our aim. And in the university to confounding with confine with the grading and grades. And so sooner or later and we're gonna full utilize this YouTube channel, and welcome back, you guys. And so let's get started. Let's get started. And my rules in my study live stream is several. First is English speaking requirement, and the second is when I feel like incompetent, I'm gonna speak Chinese. And third is that writing language in my bachelor study is German, so it is academic language in the writing style, and that's why. So there is no 1 minute 30 seconds, and so we begin now. And yesterday I cannot open flow, and they will try out and to say what is going on. And today we have several guests, and one guest is from two guests, both are from the Zoologische Garten McDonald's tree. and yesterday I meant to be by the McDonald's in the Friedrichstraße, but I haven't had to, and the reason is that we this semester starting study microeconometric analysis and macroeconometric analysis and econometric analysis. So they always aim, and that's why I try to not to first for example, like break promise and to set all the potential value into the examination, and instead of pre-eat. And I already not eat Happy Meal anymore, and the reason is that I found that it's my maticnuma. And so previous stage, and I usually only connected with the China conscious, like my back hometowns, my hometowns conscious front. And so we always using my hometown language and to express ourselves, and that's why sometimes I cannot think my living environment, like the study life in Germany, and I haven't really touched their environment, their air, for example. And also that sometimes I cannot think. But recently, since we rent this apartment, and finally we got involved into the scene, that finally we are currently actually in Germany, meine Güte. And I haven't had that feeling. The reason is that the atmosphere in Germany is quite expensive. Like if you for example, like want to transact well with your cooperative partner or your classmates, for example, and then the major problem is that the currency exchange ratio and kind of high. And if you, for example, like only bring and using your hometown store, and you feel like more happier, and you feel like you feel like grateful, and you always can have the exchange ratio behold, and the reason is that they have the equivalent value as you, and so you don't need to like pay 6 times and or 7 times in order to have to maintain the same exchange ratio in outside transaction, and so that sometimes you feel more relaxed, and so that is one way was suggested by Tiggy professor, and he suggests me to using the hometown environment to, for example, like eat the same tasted crepes in Alexanderplatz, and instead of to adjust yourself into their environment, because that is kind of time costly, and that's why that's why I think it is kind of a good way, and but reverse speaking, and for example, like you using euro, but you think like you think the cheap Chinese yuan, for example, like your hometown is not very well developed region, and that's why is that fair? Like you spend euro, but you are using kind of Chinese yuan, and you feel more happier. It is not because you feel happier, because your German environment feel much more happier, because the using one euro can seems like using 7 euro, and that's a problem actually. And but yeah. But let's jump into today's study session, and we're gonna talk less because we have a lot of things to do. And okay, cool. So let's try whether the flow gonna open or not. The flow, the note taking app. I got new clothes in. So but I gonna yeah. Tomorrow is Monday, and we yeah I gonna yeah. And we got two guests, the two pigeon, that coming through the small balcony, and as you guys can see, it is there, and I kind of stuck there because I don't know how to handle it, and I haven't saw that before in this new apartment. I was yeah, and have a little bit joke up with them, and because I really feel like very rare, and sometimes like you know that their soul is coming from the Tulugisha Garten McDonald's, and it's Leah and the Coco Maveni and two PhD from Professor Notes, and because Professor Notes was once linked with my previous Femita, and that Femita know a little bit like so, and etc. So they know how that functioning, and so and the flow can still cannot open, so we just not use that anymore, and yeah, we just were using the handwriting notes. So yeah OK fine。行，那我们现在就开始吧。然后我们今天要做很多事情，然后我感觉有不是特别舒服，因为一个方面好吧，我们 just the positive thing. Like intimacy part still be beaten, but you kind of can in simultaneous second ignore that, because the reason is the reason is the happy and non-happy happening at the same second. You can choose from that you be happy instead of the opposite, and so let's drink this chicken soup and and change the 哎呀天哪，我的天哪，这个沫怎么全部都给掉出来了？Okay, we got that. And Johnny Q as well. Johnny Q can also, and they have also this kind of, yeah. And the university 的鸟窝，然后又来了。 And so let's jump into the study content. See, we change clothes. Wait. Okay. So we still get this one, and from Primark, and yesterday in Castle, and they are saying, every time same is yeah, like yeah, okay, fine. And we need to charge phone now, and yeah，总感觉这个角度有点 shift，然后等一下，OK，这样好一点，much better。但就屏幕可能会被拍进去，不过应该没关系，只要我登录上去就可以。 哦，这样也可以，这样更好一点。OK，这样 OK。这样好多了，这样我可以输入那个学校的账号，然后 嗯嗯，OK，那等一下我们把这个换一下换回来，然后行，哎我天，OK fine. My rules also in the another platform that you should always keep thinking and you should active your brain and in every second. And so also when current environment is quiet and you 哇天呐 embedded 进去了，然后我的引体模型法它还是比较疼，然后我们争取在有限的这个时间之内，然后complete 什么就 finish 什么，然后最主要的是，如果可以和别人在，你可以 perceive 到 interactive conscious，或者是你可以 perceive 到，你可以 perceive 到 other，会叫它 like noises and etc. So you mean to be conquered air conscious in every second, so to say, my requirement, and so 然后我现在打开一下微信，我刚才又被beaten 了，因为那个因为我好像把一个东西放置错误了，然后我好像放成了一个直角形状的，然后有一点像是那个 Big Bubble Tea Store，然后就是那个走的给是 button，然后它对面的不是有一个那个 EY 的那个 symbol 嘛，然后它就是那个 EY 的 symbol 你不能动，然后那个是我的 cooperative student neighbor，然后就是 I can have 他们的那个 area can set empty，然后然后另外一个是另外一个是也我一般是那个 microwave 的那个形状。对，如果大家想看，我可以到时候再猜更点也 OK，行，我们还是according to 教授的那个视频，然后我们现在想办法，然后怎么样可以避开这种情况，然后就是你比如说有一些珍贵的这个atmosphere 或者是 environment，然后你害怕进入一些 extra force，然后去对他们进行一种这种soft 形式上面的一种破坏，然后所以你会可能采取这种方法。然后呢，不可避免的是，每一秒钟，就是一直都会有不同的人来，就是进行一个伤害。然后，但是呢，这种你不可避免的，但是你还得 continue，但是你还得继续下去。然后，所以，所以就这样，嗯，也，我家人让我去搬家，但我今天想把这个课程稍微给他全部的复习一遍，嗯嗯。这个是我昨天从那个 Chibo 然后 get 的一个就非常好看的一个杯子下面的一个铃铛，蝴蝶结铃铛，然后非常好看。然后那个 style 就非常 very female，然后不是我要的那种 type，我要一个 neutral 的那种 neutralize 就行，因为我一般来说是要就是学习的，然后所以他们，我天呐，然后他就很飞妙。其实我不是很需要那种领，然后但是，对，所以就显得有点imbalance 那种感觉。但是呢，对，Alex m a c a f 应该比较行好。我们现在就开始intensive 先 review 一下，然后 economic analysis，如果是这一周的话，就是from beginning，然后但是 claustrophobia 一种的时候呢，我是要用好的纸，然后把这些 PowerPoint 再写一遍的，然后不是这种感觉，行。嗯
given x bar with factor n. And here you see, so here is just the sum of xi, right? So we have n 15 and 15. In this point, we have minus range minus 25, below 25, something. And the green one is no, look here. The green one is 50. Yeah, look here. The green one is for a sum of 50 actors. And you see already that the probability that the sum of these here is less than 50 is by definition. Right? We have here known distribution, it cannot be smaller than minus 50. And the probability that close to minus 50 is too small. Same for plus 50, of course. Expected value is 0, to extend it around 0, you see the sum of normal, right? But now you see if I increase the number of the ends, right, it is because of the sentiment theory, right, converge or because of the consistency of the estimator, the distribution of that test statistic here, yeah, that one goes gets deeper and deeper and deeper. And this would be 1,000, this would be collapse. So you can't use asymptotically, you can't let n go to infinity, right? So for consistency, and sentiment theory, that all needs n goes to infinity. But if we let n go to infinity for beta n minus beta, or for instance, this nice estimation here, then we have no decent, non-degenerated distribution of the test. We want to have a nice, stable distribution of test statistics, like the G distribution, the normal distribution, or the F distribution, whatever that we can use for our test, right? Here, if n goes to infinity, if we do not have a proper scaling of the variable, then you see that it collapses. So here you see why we talk about square root n convergence in the context of statistics. See, if you look at this one here, if you rescale with, so you have x bar is this one here, right? This is why it's called no scaling, right? We have just x bar. This collapses. If we multiply x bar with square root n, then we have this. Then we go from here to there, right? Multiplying this here with square root n, that cancels out, remains 1 over square root n times this. And one can show that this variable, so if we inflate this difference which converge because of the consistency of the estimator to 0, if we inflate this difference with square root n, then we have the same distribution. Right? So for all these three variants, if we just multiply these things here with square root n, then it converges to the same distribution. And this is more or less what we need here for this result. So this more or less illustrates this famous result here, that if we have here a linear regression model and we have these errors and we have the exhaustion x, so that the flow is unbiased, right? Then one can show that rescaling this difference, the square root n here, which is just this one here. Here, you know that beta hat minus beta is just x prime x minus 1 and x prime u, right? We have this already. And now we do this, we multiply with left hand side with square root n, because we know beta hat minus beta has no well-defined asymptotic distribution. It's just collapsed, right? Therefore, we have to inflate this with the number of observations, with the square root of the number of observations that we do on the left-hand side, and this here cancels out, so it's equal, right? So what we can show is that this here converges the distribution to a stable test distribution. So this is normal distribution with expected value 0 and surprising and is covariant. normal, because that holds here for n goes to infinity. This is the asymptotic covariance, and the convergence rate is square root n, and this is why we call beta hat square root n or root n consistent. Okay, so look, we have asymptotic normality without assuming that it moves, which were the input here. Are right? So this is the theory of the central limit theory. We start with something not normal, but then we have a lot of them, and we add them up, and they are sufficiently uncorrelated. Here, we have a uncorrelated, right? So, and you see that this is the straightforward generalization of the central limit theory that this here n is normally distributed, right? That this here is still normally distributed here, even if we have only weak exhaustion capacitors. Right? So the situation we love, we have only weak exhaustion capacitors, so black exhaustion variables are allowed, right? And we have non-normal errors. This is all covered asymptotically. It still leads to normally distributed values. Okay? And this result explains why we still apply DNF as all those places in the purification. Even though, it's not so obvious whether the regressors are really strong exogenous, or whether these are really non-normal. Okay. So good news. Yeah, but as always, it's important to memorize that we have something once. So we have traded assumption of normality and strong heterogeneity against the large number thing we are talking about, and importantly now. Yeah.
And I think a bit more general question, but why do we have a problem when we see the distribution and we think there's just a lot of structures?
Yeah, but the problem is that if you consider beta hat minus beta, right? You want to have a hat, then you want to expect that this beta hat minus zero. Okay, so, but if you have a consistent estimator, then beta 2 under the null goes to 0, right? So the probability that you observe something which is non-zero is just 0. So you have no stable test statistic like T or F or whatever statistic to do your tests. Because under the null is always, if n goes to infinity, is always at 0, right? So you will always reject, always. Because the probability is, then I always reject.
But I do have this total certainty that it has.
Yeah, but this is a perfect certainty under the null, right? And the null hypothesis we assume to be correct, right? So just because, we will, and this is the one we always reject, right? So look, if you reject, by assumption, then why testing anyway? Right? So if you want to have a test that would be able test it sufficient, you have to think this. Right? And of course it's not, there's an indication why we have to place the number of observations, why we do this duration study, which is the end of the collapse. Right? But of course it's not by intuition obvious that it's enough to modify this parameter. Right? This is already on the from exact test, right, and to asymptotic test, then then you can apply them even under PTA function. So, and in this case, what is and you know, and time squared and whatever depends on the totality assumption of the first case. And even though line contract is that strong that you guys are only Gaussian and error component of one. You know that we still assume uncorrelated and we'll give us right? This is what we talk about next. Okay, so very close related to hypothesis, to test this hypothesis is the concept of confidence. Yeah, let us talk a few words about this concept, right? You already should know. So here is the confidence interval for a scalar beta hat. So think again, beta hat is the ordinary square estimator, right? And under standard assumptions, you know that it's t-distributed, right? So that this here is the spherical here is distributed with n minus k freedom and the number of oscillations, k is the number of regressors. This is the situation that looks like very already, you know, obviously any here not so small, right? So this looks exactly like the delta, right? Yeah, t goes down there, no matter t, n goes in pouch, right? Okay, so here is the 2.5 upper and lower one height of this G. This one is Q. Okay. So here you see Q 5% half. 5% half is 2.5%. So the probability that the value of the G statistic is even smaller than that here is only 2.5%. And it's larger than that one is also 2.5%. So therefore, the probability that something here is the probability mass between these two bands is just 90%. That's standard confidence band, 95% confidence band. Okay. Because the G statistic is symmetrical, this here is just minus that. Right? If this is 0, right? If that was 0, and always get something zero, right? So T alpha half is just minus T1 minus alpha half. Okay? This is okay, so we know that this is now G distributed, so we know that probability that this random variable here is between these limits here is exactly 1 minus alpha, right? Because left is alpha divided by 2, right is alpha divided by 2, meaning that that between limits probability is just 1 minus alpha. Okay, and now there are two ways, to look at these. One way is to, this if you use the fact that this is let me try this. So now we talk about how to interpret that probability, how to use it, right? So because it's symmetry, we have T alpha of is 1 is minus T 1 minus alpha. Okay. And now that means that we can, let us now rewrite this like this. Minus T1 alpha half is smaller than beta hat minus beta divided by the variance of that. Okay? And now I rearrange this that I solve for beta hat, then I solve for beta. Okay, so this is exactly the case when I multiply with the square root and then I add beta. So this is beta plus beta minus t1 minus alpha half plus beta then times square root. So times square root. So first I multiply with the square root of the variance and then I add beta. And then in the middle there's just beta hat. And here we have beta plus. Okay, this is one way to look at it. And the other way is I solve for beta. So actually it's more complicated now. So I just multiply it minus 1. So we have t1 minus alpha half is larger than beta with beta hat divided by the square root larger than minus 1 minus alpha half. Right, I multiply with minus 1 in order to solve now for beta. Okay? Because I multiply minus 1, this here turns around. Yeah. So this shows you that it can be written as beta hat plus t1 minus alpha half times square root larger than beta larger than beta hat minus alpha half. So this equation here is exactly that one. See? Beta hat plus minus square root of alpha half. Here's alpha half I solved before. Okay? So look, now we have two variants here to interpret the confidence band. Let's start with that one here, because it's here on the slide. Okay? So first of all, you see that that this confidence band here is random. Well, obviously, because it depends on the realization of the random. The average random. So the confidence band is random. Right? So here. Right? What does it mean that the confidence band is random? Right? Here is you estimate the squares, right? And you get some estimate, beta hat. And now, okay, your confidence band depends on where beta hat is. Okay. So to say the borders of confidence bands depend on the realization of beta hat. Okay. Now we can say, okay, this confidence band here tells me that it gives me betas where I can not reject another hypothesis that my unknown coefficient was actually level of alpha. Okay. That shows you the relation, the one-to-one relation between two sides of the test and confidence band. Okay. So when you have a confidence band and your value of the hypothesis is inside that band, then you can't reject another hypothesis that the true value is parallel. Whenever the value of the null hypothesis goes outside that confidence band, you can reject it. Okay, so let me show you this. Or remind you that when you just apply it with some arbitrary linear regression, here, look here. Is that large enough for you? Yeah or no? No. that cross-section in here. And I address a lot of salary on starting salary of a person when starting the firm, right? And that's the current salary and the starting salary. And then I have the education level, so bachelor, master, and so on. And here I have education square, that's standard input regression, right? Where trying to obtain people that spell eight helps, but we have some opportunity to return. Right? At all. But not better, but okay. So look here. Here there are the estimated coefficients, these graphs that we know what happens. Here are the standard errors of those. And the standard error, the estimated standard error of the regression. So this is what we have here. Square root of the variance. Right? In the example of the single coefficient here, the square root of the variance is just a number. That's the standard error of the estimate. Okay. The t-statistic we know is just, as you see here, t-statistic is estimated value divided by standard error. Okay, so you can get this value here by just dividing 2.8 by 0.8. The p-value of the standard statistic program, which is related to that here, gives you the probability that 2.8, estimate 2.8, even though the true value is this hypothesis. So you reject null hypothesis as constant, that regression is 0, and everything comes to 1. 1%, 5%. Here, this type of segmentation level, actually, you would get modification for that wage. I'm sorry. Again, this is awesome. Okay, so the process that the magnification is of course, if you're really interested in the null hypothesis, does education matter on wage? Which are more or less, if people show their regression analysis in their paper or in their thesis, they more or less show this, of course, not the table or the program, that's something that have learned to measure this way. Do not copy the result of a specific program in the thesis, say, right? There's no line table, emphasizing important statistics for education. All the other things not relevant. Okay. So here's just everything is anything. And of course, the aim is that you know these things, right? So, and actually because you know already what R square is. We talked about the adjusted R square, something I would like to have dropped out in every standard output because it doesn't matter. Right? We talked about that only matters if n very small. Right? And very small for interest. So standard error of regression, you know what that is in our notation? It's the S. It's the estimated variance, estimated standard application of the errors. Standard error of regression, sum squared residual, well, very suggested name. Here's something we have to talk about in the next chapter when we talk about maximized estimations. And here is the effect. The S statistic is no statistical growth test. Do you know what computation of that is even now? Be prepared. No. It may be that I showed you such a table and I ask you a question like this. Okay? Because come on, this is why we're here, right? We read papers or we want to write papers where we have things and want to interpret it. Come on. Okay. So it's not too far-fetched to ask you questions. Okay. So what is the notation of that? What would you say about this? Okay, that's very interesting. S is something that is the mobility value, the p-value of that is zero. What is the value of that? Yeah. All regressions are equal to zero. That's not that. It's just going to be wrong. So he wants the decision actual science guy would say correct after sign. So the null hypothesis of that statistic is all regressors, design constant for all regressors, all C regressors are zero. This is a null hypothesis of the standard method. In other words, when we talk about that last week, it's equivalent to saying the R square of this regression is actually zero. You might observe something from zero, of course, always observe whatever regression you do. You always observe some non-zero R square, but this is just one thing. You can reject that. You can't reject it. So, null hypothesis, this is zero, and this is zero, and this is zero. Well, it has chance. It's a multiple chance. A multiple step hypothesis. But only one equal sign. But only just this is zero. No, all of the three are zero. And here we reject. Oh wow, we reject. Finally, they are 80%. Okay, so that we can reject another hypothesis that are square zero. That we have to make an halfway of 80%. Okay, so you can interpret this p-value as a minimum requirement. So if you get here a p-value larger than 10, that means I cannot reject, but even at the 10% level, that this regression I I just showed you, bullshit. Does not explain anything about it. And it's just random, whatever. Okay? Right, mean and relative statistics here. These are three information criteria that we talk at the end of the lecture when we talk about how to specify the model. Because so far, you have the assumption you know the model. Y and X beta or above. This is something in practice nobody tells what the model is. Nobody tells you if it's big or not big or which regressors you should use, right? No. Yeah. In econometrics, you often, you maybe just assume that you know the model, right? But I think what we find in practice, we have to talk about how to decide whether we should do the guess or not. Right? Guessing is one idea, of course, right? But many of the cases on the best one. Therefore, many statistical programs regularly offer these so-called information criteria. There are one that you know from Econometrics 101 test form, a very simple, very old school, very poor test actually about the organization. Okay, just as a reminder, these are things you should know. How is this related to our public spend? What I just said. We know that there are observations of statistics of institutions that matter. Yeah. These students 400 okay. We know for the 95% level, we have since the critical value of the normal institution is 1.96. This is why in practice there are two standard errors. Right? Because those are 1.96. Right? Well, two standard errors. Suppose you will be interested in the hypothesis that, look at it. Yeah, that's the constant, right? That the constant is, so we rejected the number that it's 0. And why do we do that? Because 2 times the standard error is 0.84 or 5 something, right? And if I add and subtract 0.85 to the estimated coefficient, right? Then it obviously is not equal to 0. Right? Because then it goes from 1 something to 1 something, right? So this is a range of coefficients where I'm not sure where I cannot reject the number. So obviously I cannot reject the number of the coefficients of 1, 0. Right? Yeah. Give some feedback. I'm not sure whether you know that or not. Yeah, okay. So you look at the table and you might ask you, what about the can that be true or not? Everybody will be true. Yeah. And then I ask you, well, would it be 1 or not at the 5% level? Then everybody will say, yeah, of course not. Because 1 is outside 2 sigma band. This is exactly what we just discussed. Okay? So here you see the relation between testing, right? Can that be 1 or not? And looking at the confidence band and see, oh, look, 1 is not inside the confidence band. Therefore, if I put 2 two-sided test whether it can be 1 at 5% level, then I of course would be 10. Yeah. All right. So that's one way to do it. Right? And here is the other, right? That beta hat, the estimator here, is inside that band. You know, the problem is this is much more easier to interpret somehow. Yeah, because we don't know what beta is, so how can we say? So we don't know where that is, right? So one final remark about say something like, or even say sometimes something like, well, the confidence band here tells me with probability 95%, say, the true parameter lies within that. Okay. You agree? And you have confidence band, 95%, 95%. And now you want to make 10,000. And say, well, probability that the true parameter is that is 95%. Why should that be? Yeah.
Because the confidence interval itself is like a random variable, so we cannot know if the first what the
And you're on the right track. The confidence band is random, very good observation, but what is not random? The true parameter, right? I just made a probability sentence, hypothesis, proposition about a non-random variable. I said the probability that the true parameter is in the confidence band is 95%. That makes no sense because it's a true parameter, it's not a random variable. My estimator is an X, that's the random variable. Then I can talk about probability. But the true parameter is either in the band or not. I don't know, of course, but it's either or. It's 0 or 1, right? This is why I estimate when something tells me, no, this is something conceptual, right? If you assume that there's a true value of the parameter, I just don't know it. I can estimate it, the estimator is random. So you see that the limit here, the limit of my confidence band, as she said, this is random, that depends on my estimation. Okay? But the probability, whether my true value is in the band, the only way to state this. So okay, so this is so if you put it like this, like so that's making sense of the random. Say probability of the true value of the true parameter. But how to make that? What would be a good idea to explain someone who is not led by a position? The idea is interpretation, intuition, and confidence band. You need to do an exercise where exactly value together, how to interpret exactly value. You can do that. You can always. But how would you explain someone the idea of confidence? This is unfortunately not allowed to say probability that the true parameter is that 95%. So how to reformulate that makes sense? Yeah.
as the success rate for the confidence band, maybe with a 95% success rate or confidence interval covers the area where the true parameter is.
Perfect. Okay, here is again, you make 100 estimation of beta. Right? Each estimation of my beta gives me that. Each estimation is the and the corresponding confidence. Right? So in the end, I have 100 confidence intervals. And it and goes 100 large numbers, right? In the end, 95% of these randomly estimated confidence bands overlap with my confidence. So in 5% of these cases, the confidence bands do not, the true parameter is not within my estimation. Okay? That would be the confidence. All right. Now we know what confidence band is for. a very nice thing here. So what are that? What should that theory illustrate? We have here the two values of the two parameters, and here's the value. Right? So you estimated theta hat A and theta hat B. Okay, that's what you estimate. My coefficient for rotation and that's what you estimate. Okay. And now, in the first step, I'm naive, and I'm just looking at the composite band individually for each estimator, right? And these are just one here. That one here is for A. This is the composite band of 95%. This is the composite region for beta A, right? So with 95% probability of this range overlap true value of A of beta A. And here's the corresponding composite band for beta. Okay? So meaning that in that case, for example, here, this is outside the band, so I can reject the hypothesis that beta A is 0, and I can reject that beta A is 0. Individually. The individual t-test would, for both parameters, tell me reject enough. Okay, outside of the band.
Bundeskanzler Merz hat in Israel die Holocaust-Gedenkstätte Yad Vashem besucht. Dort sagte er, Deutschland müsse für die Sicherheit und Existenz des Staates Israel einstehen. Der Besuch ist Teil der Antrittsreise des Kanzlers im Nahen Osten. Er war am Abend in Jerusalem eingetroffen und von Präsident Herzog empfangen worden. Merz sprach die Differenzen über das israelische Vorgehen im Gazastreifen an, betonte aber zugleich, Deutschland stehe weiter fest an der Seite Israels. Am Mittag will der Kanzler Premierminister Netanyahu treffen.
Okay, you have here, for example, I could reject that beta A is that beta B is the true parameter, but I could not reject beta A. Yeah. So these are single tests. Now have the condition that, come on, no, I'm not interested. But education is and but education square is I cannot just repeat tests because I'm aware of the multiple testing problem of it itself, right? So best thing I should do is to have the F test go. Significance of having zero position where mechanically then you get up, independent, confident bands, then you see that the correlation of the regressors kick in. If you calculate now confidence bands in a multivariate case, then the covariance between the two estimators comes to play. Right? So again, of course, if you account or you have to account, if you estimate if you're interested in both parameter estimates then you have to account for correlation. Super highly correlated. Right? Then whenever you reject the one, you only reject the other one. Okay, then of course, it's very the confidence bands would be very different compared to the case that they're both independent. Right? Both are an estimator of beta A and beta are independent, unrelated, and unrelated. Right? In that case, confidence in this is just a square of individual tests because they are unrelated. Right? But in general, in practice, they are correlated. The estimators are correlated because the regressors, corresponding regressors are correlated. Right? Education is high, education squared is high. Or they're confidence correlated. Right? And therefore, the resulting coefficients are not uncorrelated. Now you can see that immediately if you would re-estimate this, leaving just education square out, then the coefficient of education will change. Right? Remember the mixed variable minus, if I throw something out, which is uncorrelated to something, then the coefficients are unchanged. But if there's a correlation, then they change. And that's what happens. But education square should be correlated. Okay, here you see how that correlation of regressors transfers into correlation of estimates and into correlation and in how the confidence bands in this here looks like. So if you have expectations and if you're interested in joint significant spaces in 2 dimensions, they are via plane. And then I have in general something like this. And look now what can happen if I have multiple regressions and I'm interested in multiple hypotheses, in hypotheses that contain more than one. Like for example, here, just think about this joint significance of not the empirically relevant thing. The empirically relevant thing is that you cannot reject both individually, right? Both are integral, but you reject the other.
就这种感觉，
When
吴竟然
the
opened，
investors are like,
天，慢点剧场，这个赛场太
remember the education where the example of the good book. So suppose you have your regression where education. No. It is actually a good example because we have done the case. We have education where knowing that both were not existent. Right? What could happen is, I'm not sure that I should do this. Maybe that work. What could happen is that we throw one verbal out, and then the other comes different. Right? So here we are not able to reject the null hypothesis individually. Both are individually. So both are within the confidence band, so to say, right, of 0. But now what happens if I throw out, so I can reject that though? I'm sure there's one way without typing in everything. So, you see, I just throw out education square. Well, it's not this, right? Yes. Ta-da! And I dropped out here. What's the name of the variable? What? It's log cell, and then log cell begin, and then C in education. I want just to re-estimate the old equation, but without education square. And now it tells me I don't know what log cell is. I don't understand, but I remember that. But you can't remember what the name of the variable was. It's really a mess. Stock salary, that's why. Okay. So I estimate inflation with stock salary. And then constant, and then stock sell again. And then education. Hopefully there's no typo. Okay. Yes, it works. Look. When I include education square, education becomes insignificant. Both were insignificant. I throw out an insignificant variable, education square, and what I get is super highly significant education. Right? What happened? This is exactly what I showed you in the comment. This is exactly that happened. Right? The individual test statistics tell you, oh, I can't be sure, I don't know, maybe it's but it's about very sure about don't start that. If you would do the test for that information, it would definitely tell you, no, I'm not sure which variable to throw out. I'm not sure whether the effect on wages sure that either education or education square, or maybe both, have an impact, right? So we are sure that both variables, that at least one of them should be in, but we're not sure which one. And exactly in that case, just relying on the individual statistics would be dramatically wrong, dramatically weak, right? If you look at the first estimate into the education square, you might have said education plays no role, obviously not. That's no education out, education square, whatever the education makes sense, right? But this was only true. But the problem was correlated two estimators, correlated estimators, and these confidence ellipse problem, which was illustrated here in this night figure. Okay? So this is why it's important to apply gas tests when you have multiple creations in other hypotheses where you're interested in the significance, for example, of a whole set. Okay. So this is the reference. Okay, let's go ahead. Question? Yeah, good.
I don't really understand how the working of the estimator influences the test so far that it says that it's not relevant, but the estimator is not relevant.
So do you got intuition? So, or you don't understand? Because it does not talk about the math.
Well, I see how.
Look, and let's go back to the example. So I guess the example wage and education, we all have this gut feeling, that the higher the education, the higher the wage on average, right? So now, if you estimate such a linear equation on wages on education, if you do education as something which is highly correlated to education, right? It's more or less the same as education, like education square. Education score method has 1, 2, 3, 4, 5, depending on the level of that education square is. Come on, something which is more or less the same, right? So then you have two regressors which are hardly to distinguish, right? So if you estimate now with these squares, then the least square estimator is able to detect, but via the f-test, there is some information content in these two variables. So please don't throw both variables away. If you will do the f-test on these examples, the f-test is definitely rejected out. Throw both education variables out. It will be rejected because outside the constitution, right? But if you only look at the individual T statistics, because you just don't know f-tests, right? Or you didn't get it as they are so similar, right? Then you will apply the individual tests. And then this picture shows the case where this combination of estimates are both individually independent. But they are individual, each of this individual equals to A. So this is the confidence band to A, and yeah, why not? Right? And beta B is also big because this is that one here. So this is exactly the situation of our equation. Look at the coefficient of education square individually, applying the t-test. Both t-tests cannot reject throwing out. But if you just use the t-test to investigate whether education has an impact on wages, your conclusion would be education plays no role. Look at the coefficients, both are zero.
But this is the part I don't get when they do have an impact on the salary. Why does the t-test say it does?
Yeah, because it cannot differentiate. It could be that in education, the effect of education is +5. Then you have -5 education square. Yeah, you could put it like this, like that. You don't know, it's more or less the same. Whether education squared doesn't matter, right? You can put down education 0. It does no harm to the bit of your regression because there's still education squared, come on. Well, that's the same education because of the time correlation, right? So the logic is sure of the joint impact, but is not sure about how to, which of the variables is really important. And that explains why the individual t-statistics are so small that they are not so huge here, but the joints are small. So I'm sure, both 0, each one, yeah, maybe. One of them, maybe, but not close. That's it. In the natural econometrics, we only talk here about the multicollinearity problem. Multicollinearity means that the regressor matrix X prime X is close to non-invertibility. This is exactly when you have linear dependent regressors. This is exactly what we just talked about, right? Education is square high correlated, meaning that the regressor matrix X prime X close to non-invertibility. Okay, that one. Okay, important to interpret effects. Now, how to interpret TNF? Okay, so, oh wow, we're running that out. So, what we learned, we talked about the X-axis, you already know from the bachelor, and the TNF, and they have some quantized like test distributions, right? What it requires is that actually what it requires is that the variables are exogenous, that the regressors are known, that the individuals are known distributed, and of course E and B, something we not talk about already actually. What we did now, what we did is that actually what we also talk about very similar to our approach when we talk about what can we do with when regressors are not strongly exogenous but only weakly exogenous and the topic discussion helps. So we have about observations, then we can show that ET and S after the normalization still holds. So we only need that the arrows in exogenous for the regressors are being exogenous, right? The regressors are being exogenous, the arrows are being exogenous, but this is there, right? So what we do in chapter 9, not in chapter 5, right? But we will talk about exactly these assumptions. So when we talk about generalized square estimation and low cost estimates and low cost standard errors, then we talk about what can we do with these square estimation, how should we deal with that when errors are heterogeneous and errors are quantum. Okay. So you see that these are, that the application of the standard TNF test, everybody implies in the right word, right? Requires still some assumption, right? And economic data, and your slide might be difficult, and you might have only relatively few observations, maybe you have not so many observations that you can rely on these things, right? And maybe you don't know, how to estimate the variance and all these things. And the solution of that here, and this is what Leah will also talk about, I hope, in the next thing, is bootstrapping. And what how bootstrapping is a new thing, right? In statistics. So whenever you have no clue about all these assumptions here, so when you have no clue about the distribution of then there are two ways to do this. One thing is Monte Carlo, and this is actually not so well. That's often applied in optimization theory or integration. There are some applications out there, but the point is that this is only applicable here when you know right? So when you know the distribution, but you know the distribution of use, but you're still not sure about the distribution of the data, because not about observation, and you're not really exogenous, then you can use this knowledge of distribution to simulate the data. Okay, so our simulation studies we did so far in the tutorial, they were all Monte Carlo simulations, right? Because we knew the distribution, right? What is much more relevant in practice when you're estimating is bootstrapping. And I would love to introduce the idea of bootstrapping, but for that we have to have more time for it. Now for that, we should. Yeah, thank you. Just that. Fine. No technical. Now, I have a very good reaction to that. So, situation. I don't know the situation, right? I have really no clue about everything, right? Then bootstrapping is really a very long way to solve this. We talk about bootstrapping the data process, bootstrap sample, bootstrap test, bootstrap measure. Yeah. So the thing is that all the exact tests, t-tests, tests will work. These require a whole lot of knowledge, right? Capability of X, the error, all our operation or something. And if you already know, not sure whether all these production holds, then you apply bootstrap. And here I have two slides on bootstraps, because there are many ways, there are many bootstraps, wild bootstraps. But these are the most dominant ones, and this gives you already that. So, suppose you're in this situation, you want to estimate this regression, right? You're interested in the null hypothesis whether gamma is zero or not. Right? But now let us assume that we don't know the distribution of gamma hat. So far, under assumptions A, B, C, T, blah, 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 we know it's T. The t test. Okay? But let us now assume that for some reason, you're not sure whether it's really a T test. Right? Whether the T statistic has really a T distribution, or whether your tests are bad, without that. In that case, do the following. So, this is called parametric bootstrap because the model is fully parameterized. Now look, we assume here that there's a variance and there's parameters here, so there's nothing unparameterized. So the assumption here is that we know the distribution still of the errors here. So this is how it works. Here's the algorithm. First step, we estimate with ordinary squared model under null hypothesis. Under null hypothesis means gamma is zero. So we just estimate the model without set. Okay? Simple as that. And then we can estimate for beta, delta, or sigma squared, z squared, and and now comes the trick. We generate bootstrap samples, and we do it like this. We have estimated the distribution of our errors. By assumption, we say the anomaly is unit, and we estimated the sigma square, and here just for simplicity, we assume that they are independent. Okay, that can all be general. This is just a statement here. So, we draw from this distribution. Okay? So, estimate distribution, now we have distribution, and now we start the random generate two stars which have the same distribution as the action under the null. Okay? So, and then next step, we use these two stars and generate corresponding Y stars. And how we do that? Look, you just plug in the block under the null. So under the null now I'm 0, so we don't need that. We just plug in theta hat at t, delta hat y t star minus 1, okay, minus 1 higher. Alright, plus 2 star. Okay, so we use these these hypothetical views where we know that they are exactly as original in order to construct us a hypothetical sample. This is okay, and now we one step back. We say, okay, now re-estimate our model under the alternative, which means just include the sets. Right? And the alternatives are like non-zero, so some sets are in the model. So we estimate this deviation here, including the set. Right? We simulated the data with our estimated values, and now that's okay. And now we take the simulated data and include the sets. When we do this, we get some estimate for gamma, right? And we can calculate some t-statistic of gamma, which is just estimated by standard error, right? So we have an estimation from our original data, and we have a t-value from our original data, an estimated t-value, when we don't know whether it's right? Statistic we have. And now we use the same thing for our hypothetical data. When we know how it's this is hypothetical data under the null hypothesis. So we know gamma is 0, right? Because we didn't do it here. So, and now look, this is the indicator function, right? So this is 1 whenever estimated t-value of my gamma of the hypothetical estimation is larger than the one I estimate. So if I estimate with my original data, with the true data, then I get some t-statistic for the gamma. Problem, I don't know whether it's true. Okay. So I use my bootstrap sample, which has the same distribution of the errors. I re-estimate it, and I get some estimate for gamma then, okay, right? And I can calculate the t-statistic for it, and then I just check, well, if for this bootstrap sample p, and p goes from 1 to 10,000 or something, right? Is this t-value where I know the true value is 0, right? I didn't include that here. How often does it just by chance happen that this t-value is larger than the t-value I estimate? Okay. And if I take the average of that, so if I just count 10,000 bootstrap repetitions, right, bootstrap samples, and then I count how often that happens, maybe 100 times or whatever, 1,000 times, right? And then I divide by 10,000 to have a fraction. How often does it happen? This idea is even larger than the one I estimated now. Right? Although I know I possibly wrong. Okay. This is why it gives me the p-value, because p-value of the 10 statistic, remember alpha, right, is I know that the null hypothesis, gamma zero is true because I simulate my data under that hypothesis. I count how often I would still reject, right? The t-value is still larger than that. And this gives me the p-value. This gives me the fraction, how often do I reject, although it's true. Alright? This is how it's works. I have a p-value on a test statistic or hypothesis without making assumptions about A, yes, yes, whatever. And this slide just tells you you can go a step further. The idea is exactly the same with the bootstrapping. You see, the only generalization which however very relevant here is called delivery consequence bootstrap. You can do this even if you don't know the distribution. Now here we saw let's draw the U stars from that distribution and then we generate a hypothetical y, we have to make our model now. And now look, we can resample it, right, just from the empirical distribution. Now we do not know hypothetical distributions we know, normal, right? We just take the distribution as it is from the data, the empirical distribution, right? We have 100 observations, we have 100 stars, right? Estimated over for that expression. Then this is the distribution. And then we draw from that empirical distribution. Okay? And it's normal or not, I don't know. And this gives me again my how and then I go just the way it is. Okay? So that's the difference between parametric and non-parametric bootstrap. That I don't make assumptions about students here, I just take the truth and it still works. It's great. Okay? So this is why whenever you're doing that's how this works. So this is why, this is of course mathematical statistic that doesn't really work, right? But this is why, and it works well. Here's the example of the relation trying to show how well that works and so on. This is why bootstrapping is more and more applied in applied work, right? Because estimate our model and then we make then we want to talk about hypothesis tests and confidence bands and all these things, And yeah, and one major critique is of course always this test does not apply for whatever. Because it's not exogenous, because it's not normal, because you have not enough observations, right? This is major critique, right? It's not if you do a regression, I'm proud of my results, and then comes someone around the corner and says, I don't trust your standard errors. I do it because look here, blah, 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 then, right? And if it's your advisor or especially in the journal, then you're lost. Right? And no, I think N is large enough. No, it's not. Okay. Solution. Okay. This is why it's more and more in the empirical world, because computers are so fast, right? The only thing was the problem, 5,000 positions, blah, blah, blah. The random number generators, also improve a lot. You can do it on your smartphone, I don't know, right? So that's not the issue now, right? Therefore, it's becoming more and more complex. Okay. Thank you for staying. This right? So we talk about the assumptions, and now instead what we talk about what happens because thank you. I upload the slide for part 2 because part 1 over. No. This works for simple linear regression or mathematical regression, and I'm only interested in one coefficient, right? But what about the general case? I mean, multiple regression model, I have more than one theta. I have, for example, theta A, theta B. You have to regress with A, B, and theta A, theta confidence bands or tests of two parameters, it is important to distinguish between single parameter tests and multiple tests. And this is a very nice thing here. What are that? What should that figure be? We have here the two values of the two parameters, and here the estimate. So the estimated has a okay, that's what we estimate. My coefficient for patient, and that's what we're squared. Okay. And now, in the first step, I'm just looking at the confidence band individually for each estimate, right? And these are one. That one here is for A. This is confidence band of 95%. This is confidence region for A, right? So with 95% probability that this range overlaps true value of A of beta A. And here's the corresponding confidence band for beta. Okay. So we have in that case, for example, here, this is outside band. So I can reject the hypothesis that beta A is 0, and I can reject individually. The individual t-tests would, for both parameters, tell me reject enough. Because they're outside of the band. Okay? If I would be here, for example, I could reject that beta A is that beta B is and the parameter that not rejected that. Yeah. So these are the single tests. And now come the conclusion that come on, no, I'm not interested in whether education and whether education square is significant. I cannot just repeat the t-tests because I'm aware of the multiple testing problem. Right? So the best thing I should do is to have the F-test. So test the significance of having zero coefficient for A square simultaneously, so that is the F-test. Then you get up, independent confidence band. Then, then you see that the correlation of the regressors thinking. If you calculate now your confidence bands in a multivariate case, then the covariance between the two estimators comes to play. Right? So again, of course, if you account for it, you have to account if you estimate if you're interested in both parameter estimates mechanically, then you have to account for the correlation between the two. Because suppose for whatever reason they would be super highly correlated. Right? Then whenever you have one, you always reject the other one. Okay, then of course, it looks very, the confidence bands look very different compared to the case that they are both independent. Right? Suppose you are in a situation where the estimator of beta A and beta are independent, uncorrelated, and nothing to do with it. Right? In that case, the confidence in this is just the square of the individual test because they are unrelated. Right? But in general, in practice, they are correlated. The estimators are correlated because the regressors, the corresponding regressors are correlated. Right? Education is high, education squared is also high. Of course, they are positively correlated. Right? And therefore, the resulting coefficients are not uncorrelated. Now, you can see that immediately, if you would re-estimate this, leaving just education square out, then the coefficient that would happen. But education where it should be highly correlated. Okay, here you see how that correlation of regressors transfers into correlation of estimates and into correlation and in how the confidence band in the here looks like. So if you have in 2 dimensions, and if you're interested in joint significant spaces in 2 dimensions, they are areas in plane. I have 2 positions here, and then I have in general something like this. And look now what can happen if I have multiple regressions and I'm interested in multiple hypotheses. The hypothesis that contains more than one design. Like for example here, just think about the testing the joint significance of 2 you see 2 things. Here we already talked about. So here, what happens here is you reject both. You reject now that both are insignificant for both individually, which actually apply the t-test. Reject both hypotheses, but this is not the list of the test. Therefore, you are not able to reject right? So here we would say that would be the example. I cannot reject the education based on role. I cannot reject that education where there is no role. But I reject that both they no role. What? Yeah. So that's somehow. So I guess I should say the other way around. So you, if that point here tells you that you can reject the individual check, but you cannot reject the joint. So you would reject individually where? If you ask data both is 0, then you cannot. But you see, this is somehow strange, right? This is not the empirical relevant thing. The empirical relevant thing is that you cannot reject both individual data, right? Both are in the term, but you reject the f-test. And this can happen when the regressors are highly positive correlated, right? So remember the education square thing. So the example is not so good because we saw both are. Suppose that the regression where education. No. It is actually this example because we have exactly the case. We have education and education square. So in our example, both were not right? What could happen is, I'm not sure whether I should do it. It doesn't work. What could happen is that we throw one verbal out, and then the other becomes different. Right? So here we are not able to reject the null hypothesis individually. Both are significant individually. So both are within the confidence band, so to say, right, of 0. But now what happens if I throw out, so I inject that though? So, not generate. Yes. let's see, in education, I want just to re-estimate the old deviation, but without education square. And now it tells me I don't know what log salary is. I just don't understand. Because I remember that, but I can't remember what the name square was. It's really a mess. Like that word now. Some salary, that's why. Okay, so I estimate equation with log salary, and then constant, and then log salary again, and then education. Hopefully there's no typo. Okay. Yes, it works. Look. When I include education square, education becomes insignificant. Both were insignificant. I throw out an insignificant variable, education square, and what I get is super highly significant education. Right? What happened? This is exactly what I showed you in comments. This is exactly that time. Right? The individual test statistics tell you, whoa, I can't be sure, you know, maybe it's but it, yeah, very sure. Wouldn't do yet test for that deviation. Definitely tell you, no, I'm not sure which variable to throw out. I'm not sure whether the effect on wages come from education or from education square. I don't know. Maybe education is zero, but then education square is not zero. Or education square is zero, but then education is not zero. Right? The least square estimator just tell me, I'm not sure. I'm not sure whether education is zero or not, if you include education square. And of course, education square are so highly correlated. Right? So the data is so similar that these squares really can just not differentiate whether the impact comes from education or education square. Well, it is very sure, we can be very sure that either education or education square you know that higher education, higher wage on average, right? So now, if you estimate such a linear deviation of wages from education, if you put education as something which is highly correlated to education, right? More than the same education, like education square. Education is more than education square, come on, something which is more than the same, right? So then you have two investors which are hardly distinguished, right? So if you estimate out these squares, then the square is able to detect by a test. There is some information contained in two variables. So please don't throw both variables away. If you would do the F test on this example, the F test definitely rejects it out. Throw both education variables out. Reject them outside the context. Right? But if you only look at the individual T statistics, because you just don't know the F test, okay? Or you didn't get it as they are so similar, right? Then you will apply the individual test. Then this picture shows the case where these combination of estimates are both individually, so they're individual, each of this individual from set A. So this is the constant band for set A, and yeah, why not? It's right. And omega B is also in because this is that one. So this is exactly the situation of our equation. Look at the coefficient of education square individually, applying the t-test. Both t-tests cannot reject throwing out, throwing out. But if you just use the t-test to investigate whether education has impact on wages, your conclusion would be education principle rule. Look at the coefficients, both are zero.
But this is the part I don't get. When they do have an impact on the salary, why does the t-test say it doesn't?
Yeah, because it cannot differentiate. It could be that in education, the effect of education is +5. Then you have -5 education squared. Yeah, you could put it like this or like that. You don't know, it's more or less the same. Whether include education or education squared doesn't matter, right? You can put down education to 0. It does no harm to the fit of your regression because there's still education squared. Education squared, come on. It's more or less the same education. Cover the time coefficient, right? So the logic is this square estimator is sure of a joint impact, but is not sure about how to, which of the variables is really important. And that explains why individual T statistics are so small, standard errors are so huge here, but the joints are small. Because
就是这种感觉。
What we did now, what we did is that essentially what we also talk about so very similar to our approach when we talk about what can we do with when the investors are not strongly exhausted but only weakly exhausted and the topic actually helps. So we have a lot of observations, then we can show that ET and assets after the normalization still holds. So we only need that one error question, what the investors are exhausted, right? The investors are weakly exhausted, the error only down to one. But this is still there. Right? So what we do in chapter 9 is not in chapter 5. Right? But we will talk about exactly. So when we talk about paradigm spread, then you can go about estimate and go about standardizing. Then we talk about what can we do with spread application, how do we do that when I was heterogeneity and I was order. Okay. So you see that these are, that is up that the indication of the standard TNF test, everybody applies in the 5 words, right? We find still some assumptions, right? And the economic data, and here might be different, and we might have only relatively observations, then you have not so many observations that you can rely on these things, right? And maybe you don't know, how to estimate variance and all these things. And the solution of that here, and this is what Lea will also talk about, I hope, in the next thing, is bootstrapping. Bootstrap is the new thing, right, in statistics. So whenever you have no clue about all these assumptions here, when you have no clue about the distribution of the errors, and therefore you're not sure about the distribution of the estimator, maybe because it's not really exhaustive, maybe because they have not enough observations to bias common results, then you use bootstrap methods to make bootstrap this. And that's what we're talking about. Okay, then there are 2 ways to do it. One thing is Monte Carlo, and it's actually not so well, that's often applied in optimization to the observation. So there are some applications out there, but the point is that this is only applicable here when you know the distribution, right? So when you know the distribution, but you know the distribution of use, but you're still not sure about the distribution of the beta, because you're not about observation, and you're not thinking exhaustless, then you can use your knowledge of distribution to simulate the data. Okay, so our simulation studies we did so far in the tutorial, they were all Monte Carlo simulations, right? Because we knew the distribution, right? What is much more relevant in practice when you estimate things is bootstrapping. And I would love to introduce the idea of bootstrapping, but for that we have to have 4 or 5 more minutes. You allow for that? Or should we Yeah? Okay. Just like okay, 5 minutes. No techniques. No. So, suppose now, just as okay, I understand. But I'm not ABC, blah, 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 we know, it's T distribution. The Gefei test. Okay? But let us now assume there for some reason, you're not sure whether it's really a T test. Right? Whether the T statistics has really a T distribution, or whether your tests are better, the down best. That case, do the following. So, this is called parametric bootstrap because the model is fully parameterized. Now look, we assume here there's a variant and there's parameters here, so there's nothing unparametric here. Okay. So the assumption here is that we know the distribution still of the errors, and here just for simplicity, that's it's normal, but that's not so. So this is how it works. Here's the algorithm. First step, super easy. We estimate with ordinary squared model under null hypothesis. Under the null hypothesis means gamma is 0. So we just estimate the model without the sense. Okay? Simple as that. And then we get estimates for beta, delta, for sigma squared, S squared, and so on. And now comes the trick. We generate bootstrap samples, and we do it like this. We have estimated the distribution of our errors. By assumption, we say they're normally distributed, and we estimated the sigma squared. And here, just for simplicity, we assumed that they're uncorrelated. Okay, that can all be generalized. But this is just to explain the idea of bootstrap. So we draw from this distribution. Okay. So we estimate distribution. Now we have distribution, and now we start the random number generator, and we tell it, look, this is the distribution we should now draw. We draw these here. So what we do is we generate our bootstrap sample in a way that we generate bool stars which have the same distribution as actions under the null. Okay? So, and then, next step, we use these two stars and generate corresponding Y stars. And how do we do that? Look, we just plug into the model under the null. So, under the null, gamma is 0, so we don't need that. We just plug in beta hat x t, delta hat y t, star minus 1, okay, zero minus 1, yeah. Alright, plus two star. Okay, so we use these hypothetical U's where we know that they are exactly as distributed as the original U's in order to construct us a hypothetical sample. This is the bootstrap sample. Okay, and now we do one step back. We say, okay, now we re-estimate our model under the alternative, which means just we include the sets. Right? And the alternatives are like non-zero, so some sets are in the model. So we estimate this expiation here, including the sets. Right? We simulated the data with our values. And now that's okay. And now we take the simulated data and include sets. When we do this, we get some estimate for gamma, right? And we can calculate some we have an estimation from our original data